Okay. All right, hi everyone, welcome to the seminar. So it's my pleasure to introduce Marilena Loverde, who's coming to us from University of Washington, where she's associate professor. So you've been at Washington for a little bit after being a faculty member at Stony Brook University, and yeah. Marilena is an expert on cosmology and using cosmological data sets to learn about fundamental physics, neutrinos, and dark radiation, which she's going to tell us about today. So thank you very much for being with us, Marilena, and why don't you take it away?
Okay, thanks a lot for the invitation. And I realize I am excited about this because there's a handful of people I can see on here who work on very related things. So some elements of this, so I'm happy to have a chance to interact with your group. And also that means that some elements of this talk might be, a bit basic for those of you who've worked in detail on this, but I'm really happy to have questions, have people stop and interrupt, and also just have, engage offline at another time, like via email or something. So today I'm going to tell you about a collection of projects that are related to studying neutrino and dark radiation properties from different cosmic data sets. So stepping way back, let me just give you the motivation for this. And the idea is as follows, that we think that in the early universe, the state of things was a very hot, thermal, dense phase. And that means that as the typical temperature and energies of particles that are interacting gets hotter and hotter, there are more and more particles that can come into equilibrium. And so, today, the typical temperature of CMB photons is 10 to the minus 4 eV. But as we go to higher temperatures, we can predict what types of things were present. And so at 500 keV, we can produce electron-positron pairs. At MeV temperatures, we expect standard model neutrinos to come into equilibrium with all of the other particles. At 100 GeV and above, in fact, all standard model particles should be in thermal equilibrium at that state. And then a question is to ask whether there could have been other light particles that are coupled to standard model particles, meaning, light enough to have been produced and still persists today at some level as a relic, that we could learn about by studying the stuff that is present. And the key point is that if particles are produced at very high temperatures and they're light and stable, so they're still around today, we can detect even really small amounts of them through their impact on cosmology. So again, a very big picture. We have our data sets are the maps of the cosmic microwave background temperature, which we analyze primarily through the 2-point function or the power spectrum. And in the next sort of frontier of CMB data is polarization data. So we have mapped the temperature anisotropies about as good as we think we can do, down to a level where foregrounds come to dominate. But polarization is something that we still are getting new data on all the time, that will give us better, higher resolution maps of the polarization of radiation emitted at recombination. So features in these data sets tell us about the amount of radiation that's in the early universe. And also the thing that I'm going to focus on is that we can learn some properties of how that radiation behaves. And as a reminder of why we can do this, today the energy density in relativistic particles like photons and neutrinos is very, very small, but the cosmic microwave background data sets are giving us maps of the universe at an earlier time when the energy budget was differently distributed, and a pretty significant fraction of that was in neutrinos. Just further motivation for thinking about this. So I've been involved in the CMB Stage 4 experiment, which is this big National Science Foundation and U.S. Department of Energy led mission to build a super CMB experiment on the ground that has many more detectors than previous generations of experiments, and get to much greater sensitivity on a number of physical things that we hope to see. So that some of the key science drivers are looking for primordial gravitational waves from inflation, as well as mapping matter in the universe, and looking for the presence of new light particles and neutrino mass, which are relevant for this talk. Now, we also expect that there's relics of these light particles like neutrinos that could be produced in the early universe are also present in the universe today. And they tell us that there's at least two types of dark matter in the universe. There's the cold dark matter that forms the backbone of structure. And then there's also some kind of hot, warm dark matter in the form of massive neutrinos. These are slices from a relatively old simulation now, but I quite like them because they illustrate the qualitative differences in the way cold dark matter particles are clustered in our universe and hot dark matter particles like neutrinos are clustered. So neutrinos have large kinetic energies, and that that kinematically forbids them from clustering as significantly as cold dark matter, so they look fuzzy. And this is a fun thing to be thinking about, as you know, because neutrinos, right now, we have a lower limit on what we expect the energy budget of the contribution to the energy budget is of neutrinos. And we have upper limits that are marching down from cosmic data sets. And we think that we should have the statistical power in this decade to detect the contribution of neutrino mass to the energy of the universe today. And the tools that we use to do this are to look at maps of galaxies and mass, here shown in slices of simulations, and to measure the power spectrum and look for signatures of the effects of neutrinos on this summary statistic. Okay, and this galaxy surveys are also doing wonderful work, and we have all kinds of great things coming up with Rubin and current DES data and DESI giving data very soon, etc. Okay, so the rest of my talk, I'm going to talk about the thermal history of neutrinos and radiation in our universe, and pointing out how we can look at two properties of neutrinos or other radiation, namely how much is there in our universe and what kind of stuff is it? And I'll be more precise about that shortly. And then I'll talk about how neutrinos or other relativistic particles impact things that we can see, like the cosmic microwave background, a little bit about large-scale structure data, and a little bit about gravitational waves. Okay, now I'll talk about a lightning review of the thermal history of neutrinos in our universe. And keeping in mind that while I will focus on neutrinos, the thing that makes them neutrino-y here is that we have an expectation for what their scattering cross-section is off of standard model particles. So we predict when they decouple. And we also have some lower limit on the mass. But most of the physical effects that I'll be talking about are things that are just due to gravitational interactions of these particles. So other light relics that might come from some other new BSM physics would show up in very similar ways. So here, as a thermal timeline of our universe, we see things getting cooler as the universe expands. And one interesting thing that happens is that at sufficiently high temperatures, neutrinos were in thermal equilibrium, and then subsequently they decoupled. And so today, there should be a cosmic neutrino background in addition to the cosmic microwave background, which was released shortly after neutral hydrogen atoms formed. And that's something that we go look for. And the game is to use data that tells us about the energy budget of the universe at different epochs in time, and try to see whether we can find any evidence of some additional constituent that might have been present in the universe at some earlier time, in addition to neutrinos, which is illustrated by this little purple sliver here. Okay, so one key point here is to keep in mind that the thing that we measure the best relic of the early universe is the cosmic microwave background radiation. And shown here is the COBE-FIRAS data showing the thermal spectrum of this, which is this beautiful black body with a temperature of about 3 Kelvin. From this, one can predict the spectrum of cosmic neutrinos, and we predict that they decoupled while they were relativistic. And at that time, their momenta were described by a relativistic Fermi-Dirac distribution, and their momenta all redshifted as 1/A. And so today, they can, even though they're probably mostly non-relativistic, they continue to be described by a relativistic Fermi-Dirac distribution, and with a temperature that's a little bit cooler than the photons. The reason their temperature is cooler is because photons were heated by electron-positron annihilation, which happened after neutrinos decoupled. And what we're looking for is whether there is some contribution of some new mystery stuff with some probably thermal distribution. That's how we make predictions anyways for thinking about it, with a temperature that's probably small compared to photons and neutrinos because we haven't seen it yet. And the reason that this stuff would have a temperature, so the idea is we have some mystery stuff that at high temperatures was in thermal equilibrium with everything, and then it decouples, and subsequently photons and neutrinos, when they remain coupled, get heated relative to the new mystery stuff by different processes that happen in the universe. For instance, during the QCD phase transition, when other heavy quarks and stuff annihilated and gave energy to the remaining standard model particles. So the nice thing about thermal distributions is that there's one number that completely specifies all of their properties. The number density just goes like temperature cubed for relativistic particles, and the energy density goes like temperature to the fourth. For something like neutrinos, which is non-relativistic today, the energy density is just the mass times the number density, but the number density, if they were froze out when they were relativistic, would just go like T cubed. Okay, so to put some numbers to this, the cosmic neutrino background today should have a number density of like 330 per cubic centimeter and an average energy density that is less than something like 11 eV per cubic centimeter. In comparison, the CMB photons are slightly more abundant, but have a lower energy density because they have no rest mass. And so their energy density continues to dilute, like 1 over the scale factor to the fourth. This thermal history gives a very simple, sharp prediction for what the relic energy density would be in any species that just depends on when it froze out or when it decoupled. So what's shown here is a plot showing the relic energy density of a particle, and it's in the units that we use in cosmology, which is we measure it as this number n effective, which is the energy density in units of a simple prediction for the neutrino energy density for like 1 neutrino. And depending on the degeneracy of the particle, it will contribute more or a little bit less in the energy density today. So things that decouple at late times around the times that neutrinos did will have the same temperature as the neutrinos, and they'll contribute about the same amount to the energy density as a single neutrino does. But things that decouple very early, for instance, at temperatures higher above the time when the temperature at which all standard model particles come into equilibrium, will contribute much less. But an amount that is predictable, and you get this firm lower bound where a scalar particle, if I have a single scalar particle, it's the smallest number of degrees of freedom I could add for something that was in thermal equilibrium with a standard model, would contribute at least this number of 0.027 to the energy density in relativistic particles today. So these are the current bounds from Planck, and what we want to do is have experiments that can reach these target thresholds. And CMBS4, I'll show later, is almost here, but not quite. CMBS4 will be able to detect, their 1 sigma limit is on this quantity, ineffective, is 0.03, and the minimum contribution here is 0.027. So we're not even reaching that one at 1 sigma, but close. Okay, so a brief summary is that simple assumptions give a firm prediction for the relic energy density in neutrinos or something else. And now I'll tell you a little bit about how we detect that. And the helpful thing is that the times in the universe that are probed by the cosmic microwave background are relatively late. Most of the data that we see is coming from redshifts of tens of thousands and below. And so the energy density in relativistic particles in the standard model is just the energy density in photons plus the energy density in neutrinos. And so what we need then is a measurement of that energy density in relativistic particles or radiation in the early universe. And Einstein's equations relates that energy density to the expansion rate h, and the expansion rate sets timescales of physical processes in the early universe. So for instance, the CMB power spectrum has all of these features in it. And one broad feature of this is the damping of these high L anisotropies. So the small scale anisotropies are damped, and that damping relative to the other scales in the problem, it depends on the age of the universe at that time. So something about what the mean free path of photons is, and as they scatter between electrons, and then the total number of scatters they could have had when the universe was a given age. So those two quantities set this physical length scale, which is a damping, and that gives a measurement of the radiation density in the early universe that is, did I not show it on? Oh, here it is. That from Planck, the 2018 Planck data is very beautifully consistent with the expected 3 standard model neutrino states. And what else do I want to say? Yeah, this is something like a 10% measurement. So what we want to do is we want to get this measurement down to better than 1%. And start detecting these additional significant figures, which would be cool. So looking for additional particles is something that we can do. And that's one of the main things that we're interested in doing in the one of the with CMBS4 data that's going to be high L or small high resolution polarization data is expected to give us a big leap here. And so what we're looking for is some additional contribution to the relativistic energy density, so that what we would see is the N effective, our measure of the energy density, in what we expect for 3 neutrinos plus something else. And then this is that same plot that I showed earlier. And here is our CMBS4 target limit right down here. So not quite reaching a single scalar, but getting sort of a two sigma-ish detection of if there were like a single vial fermion. Okay, now the great thing about this measurement is that it's purely gravitational. So anything that contributes to the energy budget of the universe that is in relativistic particles is going to show up in an ineffective measurement. So that means if there are other relativistic particles out there and they're important in the early universe, we will find them. But we won't be able to tell you anything about them other than how much energy density they have. So they could be gravitational waves or axions or additional sterile neutrinos. And from that measurement alone, it's hard to learn more about them. So now I'm going to tell you how some of these measurements can be used or how some additional information in the data can tell you something about the interactions in particles. Okay, so again, the standard thing that people have been interested in for a long time is looking for like additional light neutrinos, for instance, that might have something to say about anomalies and laboratory terrestrial experiments for neutrinos. But anything, including gravitational radiation that's produced at some time, or light axions, or I don't know, some new particle that's part of some other dark sector that has some mass, which is an EV or less, would also show up in this ineffective. And one thing that we can learn about this other stuff is something about the dynamics and self-interactions of the dark radiation that might be present. Okay. So so I told you how we can learn about the total energy density, and now I'll tell you how, by studying perturbations in the energy density, we can learn something about the nature of the stuff. And the key observation is that when we're talking about something that is neutrinos, we're talking about particles that ceased to scatter off of each other and off of other standard model particles at very early times when the universe is like 1 second old. And once they stop scattering, these are just relativistic particles that free stream out to horizon scale distances. So if I hit a blob of neutrinos and ask what happens to it, or I give you an initial blob of neutrinos, perturbation in this blob will propagate at the speed of light. On the other hand, if I'm looking at something like photons, which are scattering frequently off of charged particles in the early universe, they behave very differently. And instead of being free streaming radiation that can just travel without running into anything, we refer to them as something that behaves more like a fluid or a tightly coupled fluid. And perturbations in a tightly coupled relativistic fluid propagate not at the speed of light, but at 1 over square root of 3 times the speed of light. And so that's like a qualitative distinction between stuff that is not interacting with itself or anything else, and something that is scattering frequently. In the case of CMB photons, it's scattering frequently off of electrons. To illustrate that in a different way, this plot shows the opacity of the universe for some particles. And let's say these could be neutrinos or some other new type of dark radiation. And so this is time going this way. So I have something that at very high redshift that is interacting a lot. And so it has a large opacity. And then at some point it ceases to interact and the opacity drops to 0. Now, depending on what the interactions are doing, that transition from being opaque to transparent for these particles can be different. And for instance, for neutrinos in our universe that are decoupling from standard model interactions, that transition is relatively gradual, shown on this orange plot. Whereas if I'm talking about CMB photons that decouple once hydrogen is formed, then the hydrogen forms quickly, like there's an existence of another heavier state in some sense of the energy, the binding energy of hydrogen. So that's a scale. And once the temperature drops below that, hydrogen atoms form quickly and the CMB photons can free stream. And so the duration of this transition from something like decoupling is relatively short. But the total energy density of the stuff isn't changing during this process, but what is changing is the behavior of the perturbations. So while the universe is opaque for these particles, they are behaving like a fluid, and their perturbations are propagating at 1 over square root of 3. And they're just described by a fluid that has energy density and pressure. Once they decouple, these particles can free stream. Their perturbations propagate at the speed of light. And I need not just energy density and pressure, but a whole hierarchy of Boltzmann moments to describe the properties of perturbations in this free streaming stuff. Again, please stop and ask questions during the talk. I'm very happy to have that. Okay. So the time-dependent changes to the properties of neutrinos or dark radiation, such as the opacity, which I've plotted here, lead to time-dependent changes in the evolution of gravitational potentials. And that's going to lead to scale-dependent changes in observables. So here is an illustration of that, showing some plots of CMB polarization power spectra. And on these animations, no. Okay. The both plots show the same quantity, which is the E mode CMB polarization power spectrum. And both plots show 3 curves. One of these curves has the standard model prediction for the number of neutrinos, which is 3.046. But then they also both show cases where I've added additional contributions to the energy density in units of the expected number from neutrinos. So I have an effective changing by 1 as I go from black to blue to red. But the difference between these 2 curves is that I change, so both of them, the red curve and the blue curve and the black curve on this side, and the red curve and the blue curve and the black curve on this side had the exact same amount of relativistic particles, the same total energy density and relativistic particles, but the behavior of it is different. So on the right-hand side, I'm adding particles that are like neutrinos and therefore have free streaming. They are free streaming and their perturbations propagate roughly at the speed of light. Whereas on the left side, I'm adding new particles that are fluid-like and their perturbations propagate at a different speed. So you can see it's really visible on this plot that even for fixed total energy density, the effects on the observables are quite sensitive to what the composition of the radiation is. And now I'll show a little animation, and this animation is showing something very similar, which is showing the emo polarization power spectra. And the difference between these plots is I take one unit of an effective, so one energy density and something like a neutrino, and I change it from being either neutrino-like and free streaming in the red curve, perfectly fluid-like in the blue curve, or something that transitions between the two, something that starts out fluid-like and then decouples in free streams at some time which is observable in CMB data, which is indicated by this black curve here. So if you're looking at this, the thing that's most visible is the change in the amplitude of these peaks. That turns out to be more degenerate with other parameters. And the thing that is actually the more robust signature of whether something is fluid-like or free streaming is that there's a slight shift in the position of these peaks. So in some sense, because the sound speeds are actually the same, but because the propagation speeds are different between neutrinos and tightly coupled particles that act like a fluid, their effective horizon scales are different. And when they start to evolve is different. And neutrino perturbations can evolve a little bit earlier because their effective horizon is a little bit bigger than that for the fluid-like particles. And that pulls the other particles, pulls the oscillations and all of the things a little bit to the left. Another feature that you can find in these is are changes to the matter power spectrum. So the energy density of matter perturbations is coupled to, when at early times when particles are relativistic, at early times when the radiation dominates the energy budget of the universe, it's the perturbations and the photons and the neutrinos and mysterious new particles that dominate the gravitational potentials. So those times are illustrated on the high K parts of this plot. And at high K, I'm probing times in the universe when radiation dominated the energy budget. And if the radiation that dominated the energy budget was fluid-like, then the evolution of matter perturbations is suppressed relative to a case where the energy of the radiation is free streaming. And that's because fluid-like perturbations will enter the horizon and oscillate. And they the time average of those oscillations leads to a smaller contribution to the gravitational potential than free streaming particles that have perturbations that enter the horizon and then decay. But in the end, those particles that enter the horizon, free streaming particles that have perturbations that enter the horizon and decay, have a greater contribution to gravitational potentials and source larger amplitude matter perturbations. So if I take like a half unit of an effective and make it fluid-like, then I'm going to suppress the matter power spectrum at high K. And this suppression appears for K that are large compared to the matter radiation equality scale, and it goes away for scales that are small compared to the matter radiation equality scale. And the same thing is true if I have something that is interacting there are two curves here shown here for interacting dark radiation. And the difference between the two is the transition of the duration of the transition from interacting to free streaming, or from fluid-like to free streaming. So if I'm at scales that are, if I'm looking at wave numbers K, which are large compared to the horizon scale when stuff decouples, the matter perturbations will be suppressed, just like they are for the fluid case. But if I go to scales which have wave numbers K, which are larger, so modes that enter the horizon after stuff had already decoupled, it's free streaming, it doesn't care, it looks just like the neutrino case. But interesting, what I think is really interesting here is that a feature appears in the matter power spectrum, and the location of this feature is a bump that's around the time when the stuff decouples. And I'll explain that, but I see. Okay, the question is, hello, I presume the same would be true about dark matter neutrino interactions, right? I haven't, that's a case, that is an interesting case that I haven't thought about.
Yeah, okay. Well, I was just thinking they would be very similar, but
yeah. It may be. It's not. It's actually not something I've thought about. So I'm reluctant to speak. I'm realizing here I actually have a better plot. I have a plot that illustrates this effect better that I probably should have put in, and it's in our paper. Yeah.
I just wanted to raise this.
Okay, thanks. No, thanks. Yeah, it's interesting. I mean, I think it. Yeah, I mean, it's certainly the case that you would have interactions. Yeah, I mean, it seems like it should almost certainly be the case. I don't know if you'd have this peak. If I had dark matter neutrino interactions, I would expect that to wash out power at high scales and not change things at low scales, where that transition scale depends on the horizon size when the interaction stopped. I don't know if you'd have this peak here or not, though, but maybe. This peak appears because this peak appears for modes that enter, modes that are fluid-like enter the horizon and begin to grow and oscillate. But if they start to grow, they will evolve and grow while they're oscillating. And if they start that process before they decouple, it gives a little kick and to the matter perturbations. And that gives rise to this feature here at the decoupling time. And something qualitatively similar happens around the matter radiation equality scale, even for things that are always interacting. So they're always interacting, and so they are interacting and evolving with some oscillations, but the relative sensitivity of the dark matter perturbations to the fluid is changes as you go through matter radiation equality. In other words, the energy density of the fluid-like stuff relative to the matter density is decreasing like 1/A. So at high K, it's really important, and at low K, it becomes unimportant. And the modes that are crossing the horizon around that transition get a little bit of a kick. Okay, finally, this change in the matter power spectrum, I think, is quite neat because it illustrates also that there is, in principle, sensitivity to the duration of the transition. So for something that decouples, for instance, from self-interactions or interactions mediated by a heavy mediator, that transition from tightly coupled behavior over here and free streaming behavior over here is relatively gradual. And I get a bump, but it's kind of wide, and there's maybe a little bit of a second bump here. If that decoupling process is instantaneous, then a ringing feature appears in the matter power spectrum. And so that the difference, these two curves have a common decoupling time, but a difference in duration. Okay. Something similar appears. We also studied cases in this paper led by Thijs Brinkman, Jae-Hook Chang, Peiji Du, that also looks at not just decoupling relativistic particles, but also recoupling things. So something that starts out free streaming at very high redshifts, which should show up at the high K part of this. And then interactions begin to bring these particles into equilibrium, scattering off of each other. And then they behave like a fluid. In these cases that are plotted here, that fluid-like behavior starts just prior to matter radiation equality. So it doesn't, it changes the power spectrum in this case where it turns on and then follows the fluid-like case. Okay, now I want to shift and talk about what current data says about, current CMB data says about just specifically neutrinos. So this is work led by former postdoc working with me, Thijs Brinkman, who's now faculty at University of Ferrara, and Jae-Hook Chang, who was a graduate student at Stony Brook and now is a postdoc at University of Maryland, about to head off to Fermilab for another postdoc. And so we looked at whether there's any evidence for neutrino self-interactions or non-standard neutrino self-interactions in Planck CMB data, as well as some BAO data. And this is a summary plot from this paper that is now a couple of years old that shows joint constraints on the energy density in these particles on this axis and the decoupling time. So what this plot shows is there's a couple of contours that this has to do with adding BAO data. But there's still two distinct like islands in parameter space. There is one up here where the energy density in neutrinos is around the standard model value of 3. And the decoupling redshift of neutrinos is just bounded from below. So they must have decoupled at redshift of at least 10,000. And this chunk of parameter space is smoothly connected onto standard model neutrinos, which would appear, somewhere up here, not really on the plot. But there's actually another island in the parameter space, which is down here, which allows neutrinos to have interactions that persist until very late times, and asks and wants the data to have slightly smaller energy density and relativistic particles. So the first one is connected to standard model neutrinos, and it's just saying that we can't constrain neutrino decoupling any earlier than redshift of about 100,000 because the data is just not very sensitive to it, and that probably won't change very much. Whereas here, this is a mode where things decouple at redshift of 10,000. The second mode, for those of you who are interested in the H0 tension, if you add H0 data, the second mode disappears. So it's not a solution to that, as several other authors have also pointed out. This mode is also incompatible with particle physics data. And this is illustrated on this plot, which first appeared in this paper by a group of people who were all postdocs at Fermilab at the time. And what we've done is adapt this plot to show joint constraints on coupling and a mass depending on whether that coupling, that self-interaction was among all 3 neutrino mass states here, or just among 2 of them, or just among 1 of them. So if all 3 neutrino mass states are scattering, then the fraction of the energy density in the CMB that is self-interacting would be much larger, and the constraints are much stronger also. And if only 1 of them is self-interacting, then the constraints can be weaker. So in principle, you could have, this data shows that you could have, if you have only 1 mass eigenstate that is self-interacting, then there is like a little bit of room for self-interactions to persist until redshift of like 1 million or so, but you basically can't see anything that you would see in the CMB would lie sort of above this line of redshift like 10 to the 6. We're not really sensitive to scattering at earlier times than that. So this also tells us that constraints from particle physics on neutrino self-interactions are probably just stronger than those from the CMB. Okay, so that then motivated by this and other interests in possible tensions and dark sector physics with that same group of people. Oh, sorry, I forgot. There's one more plot. There's one more plot of constraints from that paper, which is showing joint constraints on an effective, the total number of relativistic species in units of an effective, and the interacting number here, as well as constraints on the redshift of interaction. So this just looks at different data sets. There's no evidence for something else. You can basically have up to 1 of the roughly 3 units of an effective be self-interacting. And if you make it self-interacting, it's that the self-interactions are most strongly constrained around redshifts of like 8,000 or several thousands. Whereas if self-interactions cease at very high redshift beyond where CMB is testing things, you can't see them. Or if they cease at low redshift, you also can't really see that in CMB either. Okay, so no compelling evidence for new neutrino interactions, doesn't say anything about the H0 tension, does not help with that. But you can also ask whether there could just be, suppose neutrinos are just plain old standard model neutrinos that decouple at a redshift of 1 billion. But is there, if we take that as fixed, is there room for any additional radiation that self-interacts? And so this is something we set out to do in collaboration with Thijs Brinkman, Jae-Hof Chang, and Peiji Du. This, in a nutshell, we're keeping neutrinos the same. We're looking for additional contributions to the radiation density, and we're checking for additional contributions that either look like they they decouple from self-interactions mediated by a heavy mediator, like this orange curve here, or they recouple with self-interactions, or they decouple nearly instantaneously, such as dark photons decoupling from dark radiation and some other sector would. So these are some summary plots from our paper. And the short answer is there is no evidence for any new particles. If there were, you probably would have heard about it. But it's interesting to sort of look at the degeneracy. So a key question of interest is, can you have more relativistic particles in the early universe than we thought? Can n effective be bigger than the usual constraints that are presented by Planck if we allow the behavior of the n effective to change? That is, if we allow it to be recoupling radiation, decoupling, or something that decouples instantaneously. And what you can see on these plots is that the constraints on n effective do change depending on the time that something decouples or recouples, and that does free up a little bit of room for extra contributions to the radiation density in parts of parameter space where the decoupling is or recoupling is late. And just to point out, this is something that you can do with future CMB data too. And this is an old plot just illustrating, so if I'm looking for radiation that decouples and I want to jointly constrain the amount of radiation and the epoch of decoupling, that's something that you can do. CMB is most sensitive to stuff that decouples sort of in the middle of that spectrum, not too long before matter radiation equality. And it's not, it doesn't weaken your constraints on n effective very much if you add this additional parameter, which is the decoupling time. Okay. So in the last few minutes, I'm going to tell you about some different work. So one of the things that we notice in these studies is that CMB is not very, neutrinos decouple at redshift of 1 billion, and in principle, that transition, is imprinted on inhomogeneities, but there's just no hope of seeing that. The CMB data is really telling us about stuff that happened after a redshift of 1 million. So is there some hope ever of probing interactions at earlier epochs? And the answer is yes. In principle, the presence of free streaming particles affects gravitational wave propagation, and it affects the propagation of gravitational waves with wavelengths that are comparable to the horizon. So this doesn't matter for LIGO and LISA, but it matters for gravitational waves that might show up in CMB, for instance. So this is work that was done in collaboration by Zach Weiner, who's a really excellent postdoc working with me here at the University of Washington. And the key piece is, again, this concept that the nature of the perturbations and stuff matters for the evolution of our observables. And if I have free streaming particles and I compute their stress energy tensor, that stress energy tensor can acquire a tensor piece. And so that tensor piece can interact with gravitational waves. Whereas if I'm looking at fluid-like radiation, that stress energy tensor just has pressure and energy density. And those are both scalars, and there's no tensor piece in that stress energy tensor. And so that distinction means that free streaming particles can affect gravitational wave propagation. They contribute a source term to their equation of motion, which kind of looks like a mass. And fluid-like particles cannot. So couples to gravitational waves if it's free streaming. It does not couple to gravitational waves while it's fluid-like. And one thing that's interesting, so the way that if I have free streaming particles, that enters into the gravitational wave equation of motion, and that is just a change to the equation of motion. But the net effect on our observables is different depending on the initial conditions for that equation of motion, which means it's different for observables which are inflationary gravitational waves, which were sourced at a very early time and are constant outside the horizon, and then just begin to evolve once they enter the horizon, versus gravitational waves which are sourced by some causal process like a phase transition at later times. And so just a few quick summary plots of this. what's shown here is a plot illustrating how the amplitude of, in this case, primordial or inflationary gravitational waves are damped, depending on the fraction of radiation that's free streaming. So if so gravitational waves can force this tensor piece in the neutrinos, which then damps the gravitational wave amplitude. So if there's no free streaming stuff, there's no damping. But as the free streaming stuff contributes more and more to the energy budget, there's more and more damping of gravitational waves. So plotted here are some illustrations of how the gravitational wave energy density, omega GW, is changed if I have particles. There's a little bit too many curves on here, so let's just, they all have the same qualitative behavior, so we'll just stick with one. If I have particles that if I have some stuff in the universe that begins tightly coupled, as neutrinos do, then I can look at high K gravitational waves, where I'm measuring K in units of the horizon when something decouples or recouples. And at high K, the gravitational wave amplitude is not changed. But once the stuff decouples or recouples, that affects the propagation of gravitational waves that are entering the horizon at times after decoupling, and they are damped. And so that's what's illustrated here. And the rate of that transition depends a little bit on, the temperature dependence of that interaction. So here's a big plot that shows what this would look like if we have some future super experiments that allowed us to measure inflationary gravitational waves across an extraordinarily large number of frequencies. So what's plotted is the energy density in gravitational waves. And you can pick your favorite x-axis, whether it's temperature of the universe or K or frequency. The green region here is what's excluded by current CMB data. And the pink and purple are some future experiment forecasts. So this black dashed line is a gravitational wave amplitude of something like 0.05. I think this is older exclusion. This exercise has not been done with the latest bicep data. But this black dashed line is the amplitude of gravitational waves generated from inflation. And it has some features, and these features have to do with changes in changes in relativistic species that are occurring through time. So the black dashed curve in particular shows this sharp feature here at the time when neutrinos decouple. And then it's roughly at constant during this period of radiation domination here. If I make neutrinos decouple later, then that would look like these different color curves here, which are larger in amplitude and then have a drop at later times. Question: how dependent are these features on the specific inflation model? Good. So the input here for primordial gravitational waves, so the input here is assuming just a constant tensor to scalar power spectrum, like AT, that is R times AS of like 0.01. So this is assuming a scale invariant spectrum from inflation. And if instead of something being scale invariant, it had a tilt, for instance, that would change the overall shape of this black dashed curve. And in particular, if there were like features or bumps, that could also mess this up. But this signal here, I mean, there could be so your goal is to detect the gravitational wave signal and then do the inverse problem. And you will never know which parts are from changes in the interactions amongst particles versus something that was, maybe you had a little glitch in the inflationary potential around the same scale. That's a fair point. Okay, and let me say in the last couple of minutes, so something I mentioned, that the qualitative effect of free streaming versus fluid-like particles is different for gravitational waves that are produced causally. And that's because the ones that are produced causally, they get, like, I have some violent process that's sub-horizon, and that generates this long infrared tail of gravitational waves way outside the horizon. And so there's some super horizon evolution of those gravitational waves. And so because they're evolving outside the horizon, there's way more time for the interactions with neutrinos to affect their amplitude. So the relative changes between gravitational waves with free streaming radiation versus tightly coupled stuff can be much, much larger. And you can get very strange features in the gravitational waves depending on the wavelength of the mode relative to the decoupling and recoupling transition. And that's illustrated here and really beautifully explained in a lot of nice plots that Zach made that's in our paper here. Okay, so let me wrap up. And just in summary, future CMB experiments are reaching exciting thresholds for finding new particles. And I hope everyone's as excited about it as I am. And if we look at different types of data sets that we have from CMB, but also large scale structure, there are, and in the longer term gravitational waves, there's new opportunities to learn something else about any new relic particles that might exist. So thank you.
Thank you very much. Yeah, we have some time for some questions. So does anyone want to go ahead first? Maybe I can go. Do you have a feeling if, well, one thing I was curious about with these delta N effective constraints, is there any way to draw some meaningful constraint where on some particle where you don't have freeze out? So like if it was extremely weakly coupled, you have a light particle, which, you know, is a relativistic population at early times, but it's never actually achieves thermal equilibrium. Is that sort of idea hopeless, or is there some kind of?
Yeah, that's a good question. I expect that there's someone else who knows more about the answer to that question than I do. I mean, for sure, the basic thing is true that that what you're looking for is the total energy density of a particle, and it doesn't have to be in thermal equilibrium. It's just that if it was in thermal equilibrium, you get a really good prediction for what the energy density is. So it would certainly be a model dependent statement. But I'm not sure offhand if I have a reference in mind to point you to of where someone studies those types of examples. Nikita Blinoff has done some nice work on like sort of more general model building predictions, but yeah, it's a good question.
I think I'll add to that. There are actually a lot of freeze-in whatever scenarios that produce just enough radiation. It's not thermalized. I mean, even light sterile neutrinos are not actually thermalized. I mean, that's what we say, but they're not really. Okay. Yeah, I mean, it kind of depends on the mixing angle, etc. So, so you have maybe 10% or whatever of the species that you make, and you can still constrain it with any effective. So there's nothing that says that it has to be thermalized.
Right. So I guess that's fair. I mean, and then I can point you to, I know George Fuller has examples where you don't.
Yeah, George Fuller has plenty of those. There are a lot of people doing hot axions in the last few months. Yeah.
Okay, very cool. Thanks.
I think I'll ask one question as well.
Yeah,
that's
go.
Okay. That little bump that you have in the self-interaction case, it's around KF1 or something like that. Did you put it into like an n-body simulation to see if that actually survives? Because it's only a 1% effect, and you're right. Yeah.
Yeah, it's a really good question. No, not at all. I haven't done any nonlinear modeling of this, and so two things. Yeah, like I completely agree. You probably want to throw it in n-body simulation or something, because any of these nonlinear prescriptions for taking a linear power spectrum and giving something nonlinear might depend. They're like calibrated off, with the exception of the EFT, they're calibrated off relatively smooth power spectra. So it will almost certainly smooth out and go away, but we haven't checked. On the other hand, it bumps and wiggles are things that we've seen like become somewhat washed out, but don't really move around much. For instance, with BAO. So I'd be relatively optimistic that maybe that some part of this feature would persist. It's totally small. I think the more interesting thing for near-term data is to look at just the suppression in the power spectrum, because that's It's at super high K, but it's an overall suppression, and so one should be able to get some constraints on this. I think we checked, and given the current constraints on ineffective from CMB, the change in amplitude of like the power spectrum for say Lyman alpha forest is too small to see. You know, if you take current ineffective constraints from CMB, that's already tighter than what we should have from current high K power spectrum data. But I think it'd still be interesting to look at because it's kind of complementary.
Okay.
Celine, did you have a question?
No, I did. I mean, this inspires me, obviously being in the same field. So I had, I think there would be an effect for dark matter neutrino interactions, but also with the gravitational waves. I don't know if you consider it, but for sure is this thing I call mixed damping, which is when the dark matter is decoupled to the neutrinos, but the neutrinos have decoupled. But also there is simply the case where when the neutrino physics change and as you said, later neutrino decoupling goes. I think
I'm sorry, I missed the last thing you said.
So there are two possible ways where there would be some signatures. There is one which I call mixed damping because it describes the case where the dark matter is decoupled to neutrinos, but the neutrinos have decoupled from electrons and everything, and they don't really feel the dark matter, so they're mostly free streaming.
I see.
But
So even if the neutrinos are scattering off the dark matter, I shouldn't think of that as like photons scattering off.
So there are two scenarios. There is a case where the neutrinos are free streaming, but the dark matter still interacts with the neutrinos. There is a case where the dark matter is interacting with the neutrino and the neutrino feels the dark matter. So the second case is where on this plot you see the later neutrino decoupling and you would see a change.
That's very interesting. I haven't thought about it that at all, but that's interesting.
The first scenario I think would also have consequences. A little bit spaced out too, but I think they would be impact in this figure and the one where I asked questions. So it'd be great if we could, maybe we could discuss that with Marcus and Yvonne.
Very cool.
Yeah, actually, I have maybe a follow-up question, comment is, would there be any effect here of the dark matter, even if it's non-relativistic, remaining coupled for longer, given that it's not free streaming in the same sense, but it's like being dragged along part of the fluid and then decoupling from the cosmological fluid later because it's coupled to the neutrinos.
Yeah, I think on gravitational waves, I can't imagine that there would be a signal. I mean, I guess there's two things.
Was it a question to me or
Oh, sorry, what?
No, I think it was the question to either of you, I think.
Okay.
Yeah. But yeah, something to think about maybe, unless you have a quick answer.
I think most of this is really just whatever anisotropic stress you have in the neutrino sector. And that's what sources the tensor. So you have some other interaction that could cause the anisotropic stress to behave in a different way, might be coupling the dark matter. I would imagine there'll be an effect. But my suspicion is that, yes.
Sorry, go ahead. No, you go ahead.
Yeah, but I wouldn't think that the dark matter itself would have a direct impact because they're just not relativistic. Yeah, so it will be some kind of indirect thing. It's the tensor being sourced by the anisotropic stress, and you fiddle with anisotropic stress somehow by coupling it to dark matter. Then you probably engineer some scenario where the interaction with dark matter would end up affecting the tensor signal. That's what I would think.
Yeah, okay, that makes sense.
Actually, let me add this plot too. I guess a key point is that I guess the dark matter energy density is low because this is all during the radiation dominated era, but also the effect on gravitational waves for the primordial ones is really like right around horizon cross. Oh, actually this plot doesn't show that, but the effect is happening like right around horizon crossing. So for instance, I mean, you need, it's an interaction that happens when the gravitational waves is affected by the very large scale anisotropic stress around the horizon scale. So somehow something that's even if I have dark matter that has some little anisotropic stress, it would have to generate something on very, very large scales.
Okay.
Celine just told me that she got kicked out of the Zoom call and then had to go to another meeting, so she apologizes for disappearing in a puffed way. So I think yeah, I'm aware of the time. I did want to ask one final thing, just on as a sort of an outlook question. This CMB S4 projection, what is being assumed in terms of the facilities and the timescale being in that projection, this 2 sigma projection?
Yeah, that's a good question. Sorry, I'm probably not going to get the numbers right, but one thing, I'm not sure if this is what you're referring to, but so CMBS4 will have, as illustrated here, is supposed to have these 2 sites. There's a site in Chile where there's basically just big telescopes making high resolution maps of polarization. And Chile has like a much, larger, it has access to a much larger region of the sky. And that will do like high L polarization science. And that's where this ineffective measurement falls. It's there's the timeline for CMBS4 has shifted somewhat. So I'm forgetting I'm forgetting the number of years to reach this 0.03 level. If it's like 7, I think is the number that comes to mind, but that could be wrong. There is another part of CMBS4, which is supposed to be at the South Pole. And this is going to be a combination of small aperture telescopes going after low L, like looking at 3% of the sky very, very deeply to get low L polarization. And then there will also be a large aperture telescope there that will get a high resolution map of that same patch of sky to do delensing. And some of the information from that South Pole data is also helpful for this ineffective measurement, but at like a very small level. Yeah. And so the current configuration for CMBS4, I think what's happening in the Atacama Desert is a little bit more stable than what's happening at the pole. There's like a nominal plan for what's happening at the pole, but there's been some questions about like power use and that what the final configuration at pole will be like. But that won't have a big effect on this measurement.
All right, so last chance. Anyone has a very quick question before we wrap up? All right, well, if not, let's thank Marilena again, and we can finish up there.
Okay.